As continuation of Volvo Cars' safety heritage, we are going to take a big step in safety, not only for the people in our cars, but also for the people around it. The next generation of safety leadership is about having zero collision. According to some statistics, around 90% of serious roadway crashes occur due to human behavior. Hence, autonomous vehicles are promising technologies for achieving safer roads. In our cars, we will have three different modes of operation. In drive, new level of safety will help the driver to avoid collision by providing warnings, automatic steering, and braking interventions. In cruise, if the conditions are satisfied, the driver will activate the function. Then, the vehicle controls the lateral and longitudinal motion under the supervision of the driver. During this mode, driver shall have hands on the steering wheel and eyes on the road. So we need to have the system to assess the state of the driver in order to make sure that the driver is attentive. With the help of two cameras and a capacitive steering wheel, the driver monitoring system can assess the attentiveness of the driver. Cruise gradually evolved to ride, which is the autonomous capability. When the conditions are fulfilled, the driver can activate the ride. Then in ride, the car is in control and the driver can be relaxed. During the ride, the driver is completely hands off the steering wheel and eyes off from the road. The driver can do some other activities like reading, using cell phones, but not sleeping or leaving the seat. In order to make a safe transition from ride to drive, the aforementioned system, the driver monitoring system, will be used in order to assess the status of the driver. All these three different stages are satisfied by the same system, from solving the complex driving scenarios of the ride and assisting the driver in cruise and ride. In this project, whenever we use the word safety, it is in the context of ISO 26262 or ISO 21448. ISO 26262 is taking care of systematic software failure and systematic and random hardware failures. On the other hand, SOTIF is taking care of performance limitations, insufficiencies of specifications, and so on. Let's dig more in SOTIF. In SOTIF, there are these four areas which are divided based on hazardous and not hazardous, known and unknown. The goal is to identify area 3 and then by introducing safety mechanisms and safety measures, reduce area 2 to area 1. One example for unknown hazardous scenario can be this example that mentioned by publicly available specifications. Vision system can get fooled by destroying on the road, and as a consequence, a braking intervention that can lead to some hazardous scenario. One solution is using the operational design domain. Operational design domain are restrictions that we can put on the function. It can be time of the day, environmental factors, and also geographical conditions. So in order to reduce the complexity, some will be excluded from the activation of the function. For example, due to reduced visibility, we can exclude the nights and bad weathers. Also, because of reduced exposure of the pedestrians, we can just include the highways for now. Safety critical function development starts with requirement specification on different abstraction levels. In concept phase, by performing hazard analysis risk assessment, the first level of safety requirements are specified. Later, they will be broken down to safety solution in lower abstraction levels. At the end, the safety requirements are allocated to the components and how they shall be integrated. While the software is under development, the hardware will be selected, tested, and integrated to vehicle. These vehicles are named hardware ready for AD. Now let's see why they are enablers of having safe automated driving system. There are two ECUs in each AD vehicle. Each has massive CPU and GPUs, which for example are capable of performing machine learning tasks. Having centralized ECUs is an enabler for continuous development and deployment, which leads to safe function expansion and also maintaining its safety. In order to have a safe function, there is a need to have an accurate perception of the environment. This is why diverse sensor technologies are chosen. Radars are located in front and corners. Cameras provide 360-degree vision, and then ultrasonics. Although vision systems provide us good perception in certain conditions, together with radars, we believe that LiDAR is an absolute necessity for safe unsupervised autonomous driving system. The LiDAR will be placed on top of the vehicle, which provides wide field of view. During driving in highway, in high speed, LiDAR with its unique detection range, which is around 250 meters, helps us to see far out, which will complement our other sensors. Meanwhile, there is a need for data in order to extract the critical scenarios and also use it for training, testing, and validating the ML-based softwares. When software components are implemented, they will be verified against safety requirements in different environments. When the software and regulations are ready, it will be pushed through over the air and AD will be ready to be activated. In this phase, the function will be monitored in order to increase the safety confidence on it. Continuous field monitoring and systematic data-driven evaluation and adaptation of a feature at a scale does not only enable the automotive industry to validate assumptions from the requirement engineering phase, but it also enables continuous improvement of the system in order to better meet situations which were unknown at the initial phase. During field monitoring, smart algorithms will gather the data based on selected triggering events. When there are enough evidences about Area 2 and Area 3, then we start with ODD and function expansion. This process will be repeated continuously, which lead to have a safe and better experience of the function during the time. The safety argumentation will be done based on the safety artifacts, which are gathered from design, verification, validation, and field monitoring phase. As mentioned, all these artifacts are updating in each iteration, which makes the safety argumentation more challenging. But first, let's see what does safety argumentation means. In each argumentation, there is a claim on top. In our case, it can be a safety goal or requirement, which are valid in a context. Then, through different strategies, the top-level goal will be broken down to sub-goals, which at the end they will be supported by a set of evidences. Both evidences and top-level safety objective will be updated in each iteration. Arguing for safety of such a complex and dynamic system, which evolves rapidly and iteratively, is not possible by means of classical approaches. In order to achieve this, we need to understand how to adapt the safety argumentation of AD to this new context, and what technical solutions can tackle the identified challenges at the automotive OEM's scale. This is why we defined asserted, assuring safety for rapid and continuous deployment for autonomous driving vehicle. It is a collaboration between Volvo Cars, Zenseact, Chalmers, and funded by Sweden's Innovation Agency.